So in our previous lesson, we talked about how pressure, volume, number of moles, and the temperature of gas all matter in determining each of those variables for a specific sample of gas, and how changing one will affect the others. And we talked about the four laws, the four gas laws: Boyle's law, Amundsen's law, Charles' law, and Avogadro's law, where we saw the relationships between pressure and volume, pressure and temperature, volume and temperature, and volume and number of moles. The ideal gas law combines all four laws to relate pressure, volume, temperature, and the number of moles of gas. So we define the ideal gas law by this equation here. PV equals nRT. Here, P is pressure, V is volume, N is number of moles, and T is temperature, which we've all studied in the previous lesson. A new variable in this equation is R. R is the ideal gas constant. So it is a constant variable which has a number associated with it, which we'll get to in the next slides. But its units are expressed in pressure, volume, moles, and temperature so that it can relate to all four variables of a gas. The ideal gas constant R is the proportionality constant, and its value in units depend on the units in which P, pressure, and V, volume, are expressed. So here are the various values of R. And you'll notice that their units for each value depend on the volume, the temperature, and the moles, but where they differ is in their pressure units. So we have some that are in ATM, torr, bar, and pascals. So that means whatever pressure is given in the problem, okay, whatever the unit is for that pressure, you have an R that can be used with that pressure. We have to make sure that the R has the correct pressure units so that the units cancel appropriately for that specific pressure. Now we aren't going to use these last two values of R because those are specific in more in Gen Chem 2 than they are in Gen Chem 1. So we're going to look more so at the first four where the pressure units are defined more clearly. I want to reiterate our concept of standard temperature and pressure, also known as STP. STP are a special set of conditions where the pressure is defined as 1 atm and the temperature is defined as 0 degrees Celsius or 273.15 Kelvin. We said previously that the volume occupied by 1 mole of an ideal gas is 22.4 liters, and now we can use our PV equals nRT equation to prove that. So at standard temperature and pressure, we know our pressure, we know our temperature, we've defined N as 1 mole, and now we can also define R. R would then be in units of atm to match our standard pressure of 1 atm. Therefore, plugging those values into PV equals nRT and solving for V, the volume, gets us 2.4 liters for the volume of 1 mole of ideal gas. So let's start to practice with our PV equals nRT expression. In this problem, we want to calculate the pressure in bar of 2,520 moles of hydrogen gas stored at 27 degrees Celsius in a 180-liter storage tank. So we're given here PV equals nRT, a bunch of our R values, as well as some conversions to go between a few different pressures in case we needed it. Well, we want to calculate the pressure in this problem in bar, and we have an R value that's already in bar. So if I use R that has a unit of bar already in it, as long as the units of my other variables are the same as that R value, so liters, moles, and Kelvin, those units will cancel out appropriately and we will be left with a pressure in bar and we wouldn't have to do any conversions. Now, if you wanted to practice your conversions, you are more than welcome to go with any R value that you feel comfortable with, and then getting the pressure in that R value and then converting to bar. So here we're going to define pressure is what we're looking for. P is a question mark. V is the volume of the moles, which is going to be 180 liters. N is defined as 2,520 moles. And T is originally defined as 27.0 degrees Celsius. But as with our other gas laws, we need to make sure that that temperature is in units of Kelvin. Now we can see why, because R is in units of Kelvin. So in order for our units to properly cancel, our temperature has to be in Kelvin, our moles have to be in moles, and our volume has to be in liters. So we always want to convert to match our constants. In this case, R is our constant. So we're going to add 273.15 to our 27 to get our temperature in Kelvin. And we get 315 Kelvin. So let's use these variables and let's plug them into our PV equals nRT expression. So we have P, which we're solving for. We have V, which is 180. Then we have N, which is 2520. And now we have R. We want to make sure we use the R that is in the same units as the pressure that we either have or that we want. So we're going to use 0.08314 for our R. We're then going to plug in our T, which is 315 Kelvin. And now we want to solve for P. So in order to isolate P, I'm going to divide both sides by 180. And we get pressure is equal to, well, I'm going to do 2520 times 0.08314 times 300.15. And then I'm going to divide that by 180. I get a pressure of 349.36 bar. With sig figs, this would come down to 3, so this would be 349 bar for our pressure. Let's try another one. How many moles of gaseous boron trifluoride are contained in a 4.3410 liter bulb at 780 Kelvin if the pressure is 1.220 atm? Well, let's define our variables and see what conversions we need to do, if any. So we have first pressure, volume, moles, and temperature. So our pressure is given as 1.220 atm. Our volume was given as 4.3410 liters. Our number of moles is what we are looking for. And our temperature was given as 788.0 Kelvin. So we're already given our temperature in Kelvin, meaning that we have all of our variables in the proper units. We can double check this by looking at our value of R. The value of R that we're going to want to use is the one that has ATM in it, because our pressure is in ATM. So we need to make sure our volume is in liters. It is. We're gonna find our value of moles in moles, so that's good. And our temperature is in Kelvin, which it is. So we have matched all of our variables and their units to the R value, meaning when we plug everything in, all of the units will cancel appropriately. So let's plug it in and solve. We have P, which is 1.220 ATM, times the volume, 4.3410, is equal to N, which we're solving for, times the R that we chose, 0.08206, times the temperature, 788.0. And now we solve. So to solve for N, we're going to divide both sides by 0.08206 times 788. If you wanted to simplify those first, feel free. So N is going to be 1.220 times 4.3410, end parenthesis, divided by 0.08206 times the temperature, 788. So I get a number of moles of 0.0819. And I think with the sig figs, this should have 4, so we'll add that 0 at the end. Moles. Now the interesting thing with solving for moles is the question could have also asked how many grams of boron trifluoride are there. So if we did need to go to grams, we could then convert this to grams using our molar mass. Because even though a gas is very different from a solid and a liquid, it doesn't have intermolecular forces, it still has a mass. So we could still take the number of moles of a gas in a container and we could still calculate its mass using the molar mass of the gas itself. So keep that in mind for problems that you may see on your homework for this lesson. Let's do another one. A chemist is preparing to carry out a reaction at high pressures that requires 5.50 moles of hydrogen gas. The chemist pumps the hydrogen into a 12.4 liter rigid steel container at 25.0 degrees Celsius. To what pressure in kPa must the hydrogen be compressed? I want you to try this problem independently, but in order to do that, I want to get you a proper value of R on the screen for you to reference, which I believe I have up here, yes. So here we have PV equals nRT as our equation. And for R, we have a value of 8.314 liters times kPa times moles to the -1. Kelvin to the -1. Okay, so there's your R value for you to use. So please pause your video and solve this problem independently. To start this problem, the only variable we need to change in terms of units is our temperature. So we need to take T and go from 25 degrees Celsius and add 273.15 to it in order to convert it to Kelvin. 25 plus 273, we get 298.0 0.15 Kelvin. So now we are prepared to plug in our values and solve for pressure. So we have P, which we're solving for, times the volume, which was given as 12.4 liters. That's equal to the number of moles, 5.50, times the R value that I gave in kilopascals already, which is 8.314, times the temperature of 298.15 Kelvin. Again, if you're ever concerned about if your variables are correct, we just double check our R value to make sure that everything is in the proper units and that they're plugged in correctly into our equation. If you plugged them in correctly and they have the correct units, then the units will cancel. So now we're going to solve for pressure. So I'm going to divide both sides by 12.4 in order to isolate pressure. So we get pressure is equal to 5.5 times 8.314 times 298.15, all divided by 12.4. So we get a pressure of 1099.47, and this is going to be in pressure units of kPa. Now for this problem, we should have three significant figures, so this would simplify to 1.10 times 10 to the 3 kPa. If you are having trouble with the algebra portion of these types of problems, like you tried this on your own and did not get the same answer, it's most likely coming down to an algebra and rearrangement problem. So again, as I've said in our previous lesson, if you need to, rearrange the equation before plugging in variables. So for this one, we would have PV equals nRT, and in order to solve for pressure, we would divide both sides by the volume. So that would be pressure is equal to nRT over volume. Then once you've rearranged your equation and you have your variables in the right spot, then plug in your numbers so it's easier to rearrange than if you were to plug it in originally, because sometimes those numbers can get mixed up. Okay, here's another one. I want you to try this one independently. Calculate the volume in liters of a 124.3 grams sample of carbon dioxide at STP. For this one, we need the R value for ATMs, which was 0.08206 liters times ATM per mole Kelvin. So that's R. We have PV equals nRT. Okay, so try this one independently. To solve this problem, we need to use a few bits of prior knowledge in order to start us out. The first being STP. STP tells us that the pressure is equal to 1.0 atm and that the temperature is equal to 273.15 Kelvin. So we know P and we know T. We're looking for V. We always know R because it's a constant. The other variable we need to find now is N. We're not given a value for moles in the problem directly. However, we are given grams of carbon dioxide, meaning we are able to go from grams to moles using our molar mass. So that's something that we've done multiple times now throughout this course. So to start off that problem, we need to take 124.3 grams of carbon dioxide, and we need to find the molar mass of carbon dioxide. So carbon's molar mass, 12.01, and we're going to add to that 16 times 2 because the molar mass of oxygen is 16 and there's 2 of them. So the molar mass of carbon dioxide is 44.01 grams per 1 mole. So we'll divide by that value. In order to have grams cancel and be left with moles of CO2. So we'll take 124.3, divide by 44.01, and we get 2.8244 moles of CO2. So now we have moles, we have P and we have T, and we can now solve for V. So let's do that. Our pressure was 1 atm. We're solving for V, which is the volume. Our N we just calculated as 2.8244. The R value that we need is 0.08206. And the T value comes from STP of 273.15. Okay. Solving for B or V, we don't need to do anything. That 1 is just going to cancel itself out because it's 1. So we just need to take 2.8244, multiply that by R, 0.08206, times the temperature, 273.15. So that gives us a volume of 63.308 liters. And with sig figs, this would be 63.31 liters. We get 4 sig figs from the value of grams in our problem.